Hi, welcome to the video solution for physics. This is Edexcel IAL physics January 2019 new specification WPH 11 part 2. So let's start. Question number 13. Two brackets A and B support a shelf of length 1.2 meter. Bracket A is position 0.15 meter from the left hand end of the shelf. A book is placed 0.35 meter from the left hand end of the shelf as shown. So this is the book shelf. Okay, the normal contact forces of each bracket on the shelf are equal. Determine the distance of the bracket B from the left hand end of the shelf. Weight of the book is this, and weight of the book weight of the shelf is 14 Newton. Okay, so the situation is we are given the total length of the shelf, which is you can think like that. So this length is 1.2 meter, and first of all you need to visualize all the forces acting in the system. So you have a weight of the shelf, which is of course it will be acting at the center of the shelf. So you can think that the weight of the shelf is at the center and it is acting like that. So this is 14 Newton, and you have weight of the book acting down. So you have weight of the book acting down, and the weight is 8.5 Newton given. And then you have a contact force on both support A and B. So you can think that, okay, this is the contact force at B. I'm just calling it initially RB, and at A we have another contact force which is RA. So this is the force diagram, and the condition is they are saying that the normal contact forces of each bracket on the shelf are equal. So you can say that RA equal RB. And then we need to find the distance of the bracket B from the left hand, meaning we need to find that distance from the left hand. That I'm just calling this distance as x. We need to find that. Okay, so we are going to use concept of a moment about a given point or any of the point. It's up to us or you to choose a point as a pivot, because I need to find RB here. So it's better to take point A as a pivot, because if I take A as a pivot, then there will be no moment due to RA, and then we can figure out the distance x, taking the moment about the point A. So if you take A as a pivot, that means you can see that the weight of the book and the weight of the shelf is going to produce clockwise moment. You can see the situation that due to 8.5 the shelf is going to rotate in that way. So this is a clockwise moment of the book weight, and this is another clockwise moment of the weight of the shelf, and the moment due to contact force RB will be anti-clockwise. So you can visualize something like that about that point A. So we have a 2 clockwise moment and 1 anti-clockwise moment, and according to principle of equilibrium or moment, sum of clockwise moment must be equal to anti-clockwise moment. So you can say that moment about A, so 8.5, this is the force, into pivot distance or the moment arm or the perpendicular distance. In this case, we don't need 0.35, we need distance of 8.5 to the pivot, meaning we need this distance. And clearly from the diagram you can see that this distance is 0.35 minus 0.15, which is 0.2. So this is 0.2. So you can write here 8.5 times of 0.2 plus another clockwise moment due to 14 Newton. So 14 times a pivot distance. In this case, the pivot distance of the bookshelf weight is the distance from here till here. And clearly you know that this 14 unit is acting at the center, and the center distance is 0.6. So 0.6 minus 0.15, it will give you 0.45. That means that distance is 0.45. So you can say that 14 times of 0.45. So these are sum of clockwise moment equal to anti-clockwise moment, and anti-clockwise moment is due to RB. So RB times the pivot distance, and I'm assuming that the pivot distance is x dash. Okay, x dash, and x dash is the distance of the RB to the pivot one here. This is x dash. So first I need to figure out x dash, and after finding x dash I can add 0.15 to find the required distance. So this is x dash that I need to figure out first. But in this equation I have two unknowns, RB and x dash. That means for x dash, first I need to figure out the value of RB. And how do we do that? In this case, we see the forces in a vertical direction. We equate the forces. Forces acting upward must be equal to forces acting downward. So we have two forces acting upward. So RA plus RB, these are upward forces, equals to downward forces. Downward forces are, we have two forces, 8.5 and 14. So 8.5 and 14. So you can see that this is 22.5. And we know that RA equal to RB. So you can say that twice of RB is equal to 22.5. That means RB is equal to 11.25 Newton. This is the contact force at B, and I can use this force here. So if you substitute 11.25 in place of RB, and you can figure out x dash. So x dash will be equal to, if you put this 11.25, you can put here, and then you can do your maths, you can figure out x dash. Then x dash will be equal to 0.711 meter. This is not our answer because this is the distance from the contact force RB to the pivot, and we need to figure out distance of the bracket B from the left hand. So the distance x would be equal to x dash plus 0.15, and it will give you answer x is equal to 0.861 or round it off 0.86 meter. That's how you can figure out the distance of bracket B. Part B, bracket B is moved closer to the left hand end of the shelf. Explain the effect on the magnitude of the normal contact force of the bracket B, meaning bracket B is shifting to the left hand side. So what happens? You know that we have a anti-clockwise moment due to contact force RB. And this contact force creating anti-clockwise moment RB times x dash. If you remember in a previous question, this is anti-clockwise moment. If you are decreasing x dash, that means the anti-clockwise moment is decreasing. So the shelf will not be in equilibrium. So in order to be in equilibrium, the contact force RB has to increase so that the anti-clockwise moment is increased in order to balance the shelf. So if you move bracket B closer to the pivot, that means the contact force has to increase. Question number 14. The approximate age of an egg can be determined by placing it in a bowl of water. Two eggs of a different ages are placed in water and come to rest as shown. Okay, so 1 day and 1 month, two eggs of different ages. A student searched on the internet to find the reason why old eggs float. He found that the following statements on the different website. Statement 1 is old egg float because as the eggs ages, it starts to decompose. As it decomposes, gases are produced that escapes through the eggshell. And statement 2 is as the egg ages, air enters the egg through the eggshells and increase the size of the air cell. The larger air cell acts as a flotation device and hence old eggs float. So now the internal structure of an egg is shown below. Okay, so this is the air cell. Fine. Now if you see what is happening here, statement 1 is saying that as egg ages, it starts to decompose, and when it decomposes, gases escape. This is a key point. Gases escapes through the eggshell. So what if gases are escaping? Gases are escaping through the eggshell. That means overall mass of the internal mass of the eggshell or egg is decreasing. So this statement suggests that mass is decreasing. That means weight is also decreasing because W is equal to mg. Okay, and remember, it's all about flotation, either sink or maybe float. And of course, in both cases, if you see, we have two forces are acting: weight acting down and upthrust acting upward. Weight acting down and upthrust acting upward. Okay, so that's what we need to include all these points in our answer. So as per statement 1, as air escapes, mass decrease, so the weight decrease. And statement 2 suggests that air enters. If air is entering, that means mass is increasing, so the weight is increasing. Okay, but because of the eggshell, volume of the eggshell stays same. Volume stays the same. There is no change in the volume. Okay, and remember, because we need to compare upthrust with the weight, and upthrust acting on an object, U is rho Vg, and rho is the density of the fluid, which is in this case water. It is not changing. G is acceleration due to gravity. Upthrust depends on size of the object, the volume. So volume is not changing. That means no matter air escaping or entering, volume of the egg stays same, so the upthrust stays same. There is no change in upthrust in both of the cases. So what? Now if you compare on the egg, now you have two forces acting, W and the upthrust. And you know that as per statement 1, weight is decreasing. If the weight is decreasing, then overall upthrust will be greater than W. That means you have a resultant force acting in upward direction that causes the egg to move upward. That means the egg is going to float in as per statement 1, and as per statement 2, because weight is greater, so egg should sink. That means the statement 1 is correct statement about the flotation of the egg on the website. So you can summarize all these points in that way. Question number 15. P and Q are identical spheres. Sphere P moves along a smooth horizontal surface and collide with the sphere Q, which is initially stationary. After the collision, sphere P moves off with a momentum of 0.096 kg meter per second in the direction of 15 degree to its initial direction. Sphere Q moves off with the momentum of 0.14 kg meter per second in the direction of 10 degree as shown. So okay, that means this is the momentum of 0.096 and this is 0.14 in the direction of 10 degrees is shown. So use a scale vector diagram to show that the magnitude of the total momentum of sphere P and Q after collision is 0.2 kg. It is a question about vector addition, but not the ordinary. We have to use a scale vector diagram. That means you will have to use protractor and ruler to draw a scale vector diagram. So you will have to convert these numbers into vector. They are already vector, but this is vector, this is momentum vectors, but you will have to convert this into vector in terms of length. That means centimeter. You need to choose a scale and then need to draw the vector, scale vector. So the first step is you need to choose a wise scale or suitable scale so that you can draw an appropriate vector diagram. So I guess if you see the number 0.096 and 0.14, so you will have to choose 1 centimeter is identical to 0.02 kg ms minus 1. This is our scale, and if you, it is not 0.021, this is kg. Okay, if you look at that scale, that means for 0.096 you can draw a line or a vector of 4.8 centimeter, and for 0.14 you can draw a vector of length 7 centimeter. Once you have these length, then you can draw two vectors of length 4.8 and 7 centimeter according to vector head and tail load at these angles. So first of all, you need to draw a reference line like that. This is x-axis, and from that axis you will have to measure. It's your choice whether you draw 0.14 vector or 7 centimeter vector first or 4 vector first. It's your choice. So I'm going to draw 4.8 centimeter. I cannot show here because I'm not using ruler. I'm just giving you idea. So you will have to use ruler, and you put ruler here. At that point, first you need to measure the angle of 15 degree using protractor. So measure angle 15 degree first, and then draw a line of 4.8 centimeters. Suppose this is the vector of 4.8 centimeter, representing the momentum 0.096 at 15 degree, and then you will have to draw head of the first vector joined with the tail of the second vector, which is for Q. So you need a reference line, so you can draw another angle. This is your another reference line, and then this 10 degree below the horizontal one. So now you will have to measure the angle from here. You need to put the protector here, and then you need to measure 10 degree angle like this. This is 10 degree, and then draw 7 centimeter. Draw a 7 centimeter long vector, something like this. It will be something like that. So this is 4.8 at 15 degree, and this one is 7 centimeter at 10 degree below the horizontal line, and it is head to tail rule. That means you are adding these two vectors. Clearly the resultant vector is tail of the first, head of the last, like that, and you mark the arrow. This is your resultant vector. If you measure this length from the ruler, so this length will be around 11.4 something or 11.5 centimeter. I'm taking 11.5 centimeter. That's what I assume. Yeah, I guess it should be around 11.5. So this is the value of your resultant vector in terms of centimeter, and then you can convert 11.5 centimeter as per your chosen scale into momentum. If you use this scale, you convert 11.5 centimeter into the momentum value, so you will get the answer for that is around 0.231 kg ms minus 1, and you can round it off. You can say that the resultant momentum is 0.231 kg ms minus 1. That's how you can find the resultant momentum after collision using a scale vector diagram. Remember, all these workings should be done using ruler and the protector. There is no approximation. Make sure that you use sharp pencil and you put protector at accurate places. This is your final answer, 0.23 or 0.231. State the principle of conservation of linear momentum. A typical question about momentum, they ask the statement. So you will have to say that the total momentum, sum of the total momentum before collision is equal to sum of the momentum after collision. But don't forget to mention the absence of external force. That's the most common mistake students generally do. They forget to write, or students forget to write the condition of absence of external force. So don't forget to mention the absence of external force. This is the key point. So 1 mark for that statement and 1 mark for saying sum of momentum before collision is equal to after collision. Calculate the initial velocity of sphere P. Initial velocity of sphere P. So you know the final momentum, and initially only one particle or only sphere P was moving. So mass of the sphere is giving. So you say that the momentum, initial momentum of sphere P is mu, which is equal to the total momentum after, and we found 0.23. Clearly mass is given, which is 0.12. You can find u, and once you do that, so u is equal to 0.23 divided by 0.12. So mass will be 1.92. Sorry, not mass. I'm sorry. Velocity will be 1.92 meter second inverse, or 1.9 if you round it off. Yeah, it's fine. Question number 16. In 2016, the European Space Agency sent the Cephali probe to Mars. I don't know how to pronounce that. Okay, there's some probe and the name of some person. Okay, probe to Mars. As the probe approached the surface of Mars with the vertical velocity component of 460 meters per second, a parachute was opened to reduce the speed of the probe. Once the vertical velocity of the probe had reduced to 75, the parachute was removed and the thrusters were switched on. Due to an error, the thrusters were switched off too soon, leaving the probe to free fall to the surface of the Mars. So this is the condition, and these are the respective velocities of a different position. The parachute was used over a decrease in height of 9.7 kilometer, show that the average vertical acceleration of the probe due to the parachute was about 11 meters per second. A typical question for the first stage, that distance is given 9.7 kilometer, and you need to find acceleration. So we are going to use SOAT equation, or equation of motion. Distance given, we need to find acceleration. We have initial and final velocity. So we know that v square is equal to u square plus 2as. And then we can figure out acceleration as v square minus u square divided by 2s, and v square is final velocity, which is 75 square, minus initial velocity 460 square divided by 2 times of distance. So 2 times of distance is 9.7 kilometer. Don't forget to convert kilometer into meter. This is 9700. Once you solve the right hand side, so acceleration will be equal to minus 10.61 or 10.61 or 10.6 meter second minus 2. This is your acceleration during the first fall due to parachute. Part 2. The parachute was at an angle to the vertical as shown. This is the vertical line, and this is the total resistive force acting on the parachute and probe was at an average angle of 6 degrees to the vertical. Calculate the magnitude of average total resistive force. You may neglect the mass of the parachute. So mass of the probe is 600. Gravitational field strength on Mars is 3.8 Newton. Now you can see that if you see the number of forces acting, in this case we are ignoring mass of parachute. So we have weight of the probe acting downward. This is the weight. We can find weight as 600 times g, and in this case g is not 9.8 because it's all about mass. G on the surface of Mars is 3.8. So W equal to mg. Remember, this g is not 9.8, and the other force acting is along that line making 6 degrees. This is the resistive force F. Clearly you can see that you can resolve the force into its component, which is parallel or cancelling the weight. So if you resolve this force into component, then you have a force component of F in that direction like that, and this component is adjacent, and this is adjacent component, so it will be F cos 60. Sorry, it's not 60. Sorry, it's 6 degrees. So F cos 6. So we know that due to the parachute we have acceleration, and we calculated this acceleration in the previous part, minus 10 point something, I guess 6 meter second. That means we have some resultant force acting on that probe. That means weight is greater than F. Because of this acceleration, we have resultant force. If we have a resultant force, then we have a net force. That means we can write that W minus resistive force is equal to resultant one or resultant force, which is MA. Clearly, I can find F if I rearrange this equation, and if I rearrange this equation, then I can say that F is equal. It's the one. Another important point is, because we are comparing the vertical forces, so it should not be only F, it should be F cos 6. So W should be greater than F cos 6. So I can rearrange this equation for F, and I can say that F is equal to MW minus MA divided by cos 6. So F is equal to W is mg, and m is 600 times 3.8 minus m is 600 times acceleration, so minus 10.6 divided by cos 6. And if you solve this equation, so the resistive force F will be equal to around 87.59 Newton, and you can round it off to 8690 if you wish. So you can leave it here, or because we are giving 3 SF, so we can say that this is 8690 Newton or 8687, it's fine. This is the average resistive force. The probe was in free fall for a height of a height of 3.7 kilometer, reaching the surface of the Mars with a velocity of 150 meter per second. Explain whether the term free fall is correct in this context. Your answer should include a calculation. Gravitational field strength on Mars is 3.81. So you need to see first the situation as per your diagram, given diagram, and the diagram is this. Now, if you see the situation, what is going on here? So they are saying that the probe was in free fall for, so they are talking about this last interval. So this interval is 3.7 kilometer, in which you have change in velocity from 68 to 150. That means it is accelerating, speeding up. So can we say that this free fall is this downward motion of the probe is a free fall? Remember, the word free fall is only used when the force acting on a falling object is only the gravitational force. Okay? Gravitational force, or you can say the weight of the object. If the only force acting on the object during fall is the weight or the gravitational force, and the acceleration of the object is equal to acceleration due to gravity, then we say that it is a free fall motion. But if there is another other factors are involved, some other resistive forces are involved, or whatever, or acceleration is not equal to the acceleration due to gravity, then it is not a free fall motion. Okay, so first we need to figure out whether the acceleration during this fall is equal to acceleration due to gravity at the surface of the Mars or not. If acceleration in this interval equal to 3.8, then we would say that indeed it is a free fall. If it is greater or less, then it will not be a free fall. So first we need to figure out the acceleration. And again, we have a distance, we have initial and final velocity. We use same approach. V square is equal to U square plus 2AS, and we can figure out acceleration. If you use this equation, this is your U, this is V, this is the distance in kilometer. Don't forget to convert into meter. The acceleration you will find is 2.4 meter second minus 2. Clearly, during this fall, the probe has acceleration 2.4, which is less than the acceleration due to gravity at the surface of the Mars. That means it is not a free fall motion. So you can combine all these calculations with the statement in this way. So free fall motion means the object should fall only influence of the gravitational force, and the acceleration must be equal to the acceleration due to gravity. In this case, it should be 3.8 meter per second square, but the probe is falling. This we have shown this calculation before. The probe is falling 2.4, which is less than the 3.8. That means it is not a free fall motion. Thank you very much. I hope you enjoyed. See you in the next part.